Hello, welcome to Friday's edition of Cracking the Cryptic. It's a beautiful day here in the UK. The sun is shining, and it's shining on me as well because I'm about to attempt a puzzle that looks fascinating, and I've had to train to be able to solve, or to be even able to attempt to solve it. This is Christoph Seeliger's Equal Sudoku. Now, Christoph Seeliger is a name that will be known to any of you who've been following the channel for any amount of time. He's got more talent in terms of puzzle construction than you can shake a stick at. He's an absolutely brilliant constructor. You may remember him, for example, from the Killer Sudoku with no numbers in it, which I tackled a few months ago. It's been one of our most popular videos. This one, this is a fascinating idea for a Sudoku, and I'll read you out the rules in a moment. There are a couple of things I want to mention first. Firstly, just to show you the sort of emails sometimes we get from even very brilliant puzzle solvers and setters. Last night I got an email from Ryotaro Chiba suggesting that it might be a good idea on the channel to have a go at this Slitherlink puzzle, because it only took 6 world-class solvers, including him, an hour to solve it. Now, so he thought that this might make a good video. Well, it would make a very long video, Ryotaro. Look at this puzzle though, it's by Pleiades, and if you squinted it, I'm not sure you'll be able to see, but each one of the sort of little areas in the Slitherlink spells out easy and hard. How clever is that? Absolutely brilliant. I think this is part of a series actually of sort of super large puzzles that some of the Japanese puzzle makers have been putting together for these boss rushes that they're doing during lockdown. So anyway, I'll put a link under the video in case any of you have a deep desire to try the puzzle. I believe it's brilliant, so that you've got every reason to. What else? Do try Prasanna Seshadri's 14 variant Sudoku that is over on our Patreon at the moment. It's free. You can just click the link under the video to go and find it. The reason it's on Patreon is that we want to give you guys a chance just to learn the rules of the puzzle before we try and solve it in a video. So check that out. Right, let's get back to Christoph's puzzle and let me tell you about it. So this is an old puzzle actually. This appeared 7 years ago on a Facebook group that I'm a member of for handcrafted puzzles. And apparently Christoph says it was the hardest puzzle he's ever made for that group. It took the best time of the world's best solvers to solve this puzzle was 19 minutes. Now let me tell you, that is an extraordinarily large amount of time. The very best in the world are crazy quick. He said a number of the world's best solvers took over an hour to solve this puzzle. Now, I have done a training puzzle. This is an equal Sudoku, by the way, so I'll tell you the rules in a second. I've done a training puzzle, so I can understand a bit now why people struggled with this. It has a lot of interesting logic that just doesn't come up in normal Sudoku. So the idea is that normal Sudoku rules apply, but in each coloured region, the sum of the even digits equals the sum of the odd digits, and digits may not repeat within a coloured region. So it's essentially a killer Sudoku, but with this odd-even equality about each of the cages. And I mean, it's a fascinating idea. And when I was doing the puzzle that Christoph recommended I do before I try this one live, I discovered all sorts of things that never occurred to me initially. I'm going to share them with you so that you guys are on the same page as I am. So the first thing to note is that each cage has to be a multiple of 4 in terms of its sum. Now, that might not be immediately apparent to some of you, but the reason is that if we, for example, if we consider the, I don't know, let's look at this box down here. Let's say that the even numbers sum to x in this box. Well, we know that because that's even, we could write x as 2y. So we've got half the sum of this box is equal to 2y. Now the odd numbers we also know will therefore equal 2y. So the whole box equals 4y, which is why it's divisible by 4, because y is obviously an integer. Now, that's the first thing to note. The second interesting thing is that every cage in this Sudoku has to have an even number of odd digits. Now, again, this is quite obvious once you think about it, because obviously you can't make even numbers add up to odd digits. So we have to change, if you like, the parity of the odd numbers, and the way to change odds to evens is to add them together. But you have to add them together an even number of times, and that leads to certain deductions you can make in terms of the cage patterns. So if we look, for example, at a 5-cell cage, that must have 2 odd numbers and 3 even numbers, because you can't make 4 odd numbers equal 1 even number. That's impossible, given that you can't repeat the digits. And you know, that sort of logic applies throughout the puzzle. Anything else I want to tell you? Yeah, I mean, it's another thing that's completely obvious when you think about it is that odd digits, if you add up all the odd digits between 1 and 9, so 1, 3, 5, 7 and 9, you get 25. If you add up all the even digits, you get 20. Now that can be important in terms of doing the sort of mental arithmetic required to solve these sorts of puzzles. Now, with all that said, I'm now going to try this puzzle for you live, and do click on the link under the video to have a go yourselves. This will probably be a long one. Let us go. Let's get cracking. So how do we start this? Things I've noticed when I did the last puzzle were the 3 cages are quite restricted because they can't contain 2s or 9s. And that's obvious once you think about it. A 3-cell cage, we know it's got to have 2 odd numbers, because you have to change the odds into an even number. So it's got to have 2 odds and an even, and therefore you can't have a 2 as the even digit, because then the 2 odd numbers can't add to 1. They both have to be 1, and obviously you can't repeat 1s in a Sudoku. So there's no 2, and similarly, for the same reason or a similar reason, there's no 9, because the minimum, we know there's 2 odd digits, so we'd have to add at least 1 to that, and we can't use the even digit 10 in a Sudoku. So that is another little thing to bear in mind. So first thing I'm going to have a look at is the 3-cell cages and see if any of them interact with each other. And they don't. I don't think they do anyway. These... No, I'm not sure that's the place to start this. Right, the other thing we could do is look at the big cages then. So we have down here an 8-cell cage. And that is very interesting. Let us think about an 8-cell cage. So we know an 8-cell cage will have to contain 4 odd numbers and 4 even numbers, because we can't include an odd number of odd numbers. So if it includes 4 even numbers, it includes all of the even numbers, 2, 4, 6 and 8. 2, 4, 6 and 8 add to 20. So we must ensure that odd numbers add to 20 in this cage. And the only way to do that is to remove the 5. We said at the start that the odd numbers add to 25, so I remove the 5. There is no 5 in this region in the bottom left. So there must be a 5 in one of those 2 places in box 7. How cool is that? So now there's a 5 in the 7-cell cage. Okay. But yes, this box. Let's look at box 9. Now here in box 9 we've got a 5-cell cage and a 3-cell cage, but we can view those as an 8-cell cage because of the logic that we're using here. So we know that the odds and the evens add up to the same number in this 5-cell cage. We know the same is true for the 3-cell cage, so when we combine them, we know that the odds and the evens will be equal to one another. Therefore, this cage has the same logic as this cage. And that means there cannot be a 5 in the 8-cell virtual cage that we've drawn. So that square is a 5, and we have a digit in the grid, and we have a digit in a 3-cell cage. So the way to think about this, I guess, is to think what odd digit can join the 5 in this cage. So we could join it with a 1, that would be fine, and then the even digit would have to be a 6. We could join it with a 3, that the even digit would have to be an 8, but we can't join it with a 7, because then the even digit would have to be a 12, and you can't put a 12 in a Sudoku. So we don't actually get much of a restriction there. We know this 3-cell region now doesn't contain a 5, and we know it can't contain a 7 and a 9. If it contained a yeah, that's interesting, isn't it? Because it can't contain a 3. Well, it can contain a 3, but only with a 1. Because if we put a 3 and a 7 in there, we can't put a 10 in the even number. So we actually know that this has got a 1 in it. Therefore, that is not got a 1 in that square. Therefore, that square can't be a 6. I have no clue, Christoph, how you came up with the idea of creating puzzles around this constraint, but it is what I love about it already, and I've only done one puzzle like this before, is that it makes you think in completely new ways. Obviously, there is the sort of standard Sudoku paradigm sort of going on, but this whole odd-even thing is just completely new. Now, what can we do next? So in this box, I can see we've got a 4 cage and a 3 cage completely within the box. So that is a virtual 7 cage. And that virtual 7 cage is more interesting to me than this one and this one, because this one is all in the same box. So there's going to be, if I can work out what the outies are here, then I'm going to know where they go. Now, can we do any arithmetic on a 7-cell cage? Well, it's going to be complicated, isn't it? Because we know that every cage adds up to something that's a multiple of 4. So it obviously can't add up to 44. I mean, I hope it goes without saying that the numbers from 1 to 9 add up to 45. So if we're missing 2 of those numbers, we can't add up to 44. If we add up to 40, on the other hand, yeah, okay, this is not too difficult to do. So if this virtual 7 cage added up to 40, then the even digits would have to add up to 20. So that would include all of the even digits. So actually, it's impossible, because we know, therefore, that there would be an odd number of odd digits in this cage, which is impossible because they won't add up to an even number. So 40 doesn't work. If this 7-cell cage added up to 36, the even digits would add up to 18. So that would mean they were missing a 2. And the odd digits would therefore have to add up to 18, so they would have to miss a 7. So one possibility is that there is a 2 and a 7 in those 2 squares. If we go to 32 though, then we need to remove a 4 from 32. Obviously you halve it, you get 16. therefore you need to miss out a 4 from the evens and a 9 from the odds, because the odds add to 25 in total, and we can only miss one of them out. So, and if we go to 28, 14 would be what we need the evens to add up to. That would miss a 6. Yeah, okay, but the odds don't work, because there we have to miss out 11 with one cell, which we can't do. So that we know actually, yeah, and we know more actually, because we know that the missing digits here are 2, 4, 7 and 9, but we know that a 3-cell cage can't contain a 2 or a 9. So that can't be a 4 or a 7. So we are starting to get somewhere. Although I'm not exactly sure I know how far we're getting, because how on earth do you tell which way round this goes? So if this was 7, this would have to be 1, 8. So 1, 8 would go in there if this was 7. If this was 4, this would have to be 1, 3. So this becomes 1, 3 or 8. The 5 therefore must go in the P pentomino at the top. So if this is 4, this is 9. That would put a 9 in here. If this is 7, this is 2. That would put a 2 in here. If there was a 9 in there, that would add, the odd digits would add up to 14. So you'd need 3 even digits to add up to 14, which would be 8, 2 and 4. That's possible. 5. Sorry about this. I need to do some thinking here. 8. So what am I meant to deduce from this? If this was 7 and 2, no, this could still be 1, 3, 4. That would be fine. 3, 4, 7. Maybe I've got to look somewhere else here. This is not actually. So in all of the 7-cell cages, I'm missing either a 7 and a 2, or I'm missing a 4 and a 9. So problem is there's so little information. We've got one given digit. So, got 5 digits that are just not in regions. Now that actually is a little bit suspicious. That is a bit suspicious. Right, what I'm going to do, I'm going to check something. So what I'm going to do is I'm going to add up all of the odd digits in this grid, because we can do that, because we know what every cage is going to have. You know, the P pentomino has got to have 2. This has got to have 4s. So 2, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 20, 24, 26, 28, 30, 32, 34, 36, 38, 40. That's very interesting. 40. So the coloured regions have 40 odd digits exactly. So how many odd digits are there in a Sudoku? Well, it's got 9 rows. We know in each row there are 5 odd digits. So there are 45 odd digits in a Sudoku. Therefore, these are all odd. My goodness me. Now this is going to be nice now. Look, we get the 9. That can't be a 2 anymore. That has to be a 4. So that shifts a 9 into there. And so now we know that the odd digits in the P pentomino sum to 14. We need 3 even digits to sum to 14. There's only one way of doing that. So that is forced to be 8, 2 and 4. That means there's no 8 in here. So this becomes 1 and 3, which we could have got actually from just thinking about the 4 being in the 3-cell cage. These two are 6 and 7 to complete the box. 7 is interesting immediately to me because the 7 is in a 7-cell pentomino or 7-cell septomino or something. 7, you know what I mean. Now, so that means that this one has to contain a 2 and it doesn't contain a 4 or a 9. Oh, hang on. No, I can do better than that because, in fact, look, there's a 6 in this septomino. Is it sept or a heptomino? I don't know. But as there's a 6 in here, where do I put the 6 in this box? It can't go in the blue region because it would repeat in the 7-cell cage. So it must, and it can't go in there. We know that's an odd digit. So the 6 goes in there. And we know that the blue region doesn't have a 4 or a 9 in it. So the 4 must also go in here. And now the even digits in this tetromino sum to 10, so they need a 3. There's got to be a 3 in there in order to make the odds and the evens equal. And we actually get somewhere here. This is amazing. So now we've got a 3, 4, 6 triple in this box. Let me get rid of the 3, 4, 6 from there, and the 4, 6 from there, and the 3 from here. And the 9 can't be in the blues, so the 9 is in the purple again. And 2 9s in the purples. And now let us think hard about this. Now look, there's got to be a 3 in this region. Where does it go? Well, we've got 3s here and 3s here, so that's the only place that 3 can go in the blue region. 6, 7. Okay, so 9 can't be in that square. 3 is definitely in one of those two positions. 6, 7 here. So this 3-cell region can't contain a 4. How does that restrict it then? Can it? So what's the best way of trying to articulate what it could be? Well, it can't be 1 and 3 anymore, therefore, as the odd digits in here, because that would require a 4. So it could be 1, 5. No, it can't be 1, 5 and 6. Because we've got a 5 and a 6 already in the column. So if this was 1, 5 and 6, this square would have to be a 5 and a 6 simultaneously. And we don't like Schrödinger cells. So this is not 1, 5, 6. If it's 1, 7, 8, that would put a 7 in that square. and this would be 1, 8 in those two squares. It can't be 1 and 9, so it's got to then be 3 and 5. And if it was 3 and 5, the 5 would go there, and that we'd need 3 and 8 on this side. So this is always a 3, 5, 8 triple or a 1, 7, 8 triple. And that gives us a 1, 3, 8 triple in the column. Which, now that's nice because that gives us 7 digits. So this can't be a 1 anymore at the bottom. And these two squares have got to be 2 and 4. And that one can't be a 2 because that's in a 3-cell region and it would be the only even digit. So that is actually 4. So there's a 1 in here. So this is a 4, 1, 3. Good grief, we are actually making progress with this. This can't be a 3 now. This, if this is not a 3, this is not an 8. It's not 3, 4, 1, 3 pair in column 8. There must be an 8 in one of those two squares. So this is 6, 7, 8, 9 in some order. I don't think that's giving me anything useful. Okay. Right, so we're going to have to think more again now. There must be a 1 in this 3-cell region because there can't be a 3. And if we try and include 5 and 7, obviously it breaks immediately. So there's a 1 up there. Doesn't really help. So maybe it would be useful to establish whether this is missing a 2 and a 7 or a 4 and a 9. So is there a way of doing that efficiently? Oh, I tell you what, look, spotted something. Look, there's a 3 here. So whether this region is missing a 2 and a 7 or a 4 and a 9, it's not missing a 3. So the 3 must be in one of those 5 cells. So this square can't be a 3. That square has to be a 4, therefore that one is a 3. Now, does that tell us anything useful? Answer, I'm not sure. So if this region has no 7 in it, you can see this 7 suddenly becomes massively powerful. Because it would put a 7 there in box 8, and it would put a 7 there in box 5. And does that cause us a problem? Yes, it does. That doesn't work. Because now I know the red region here has no 2 or 7 in it in this sort of hypothesis. So where do I put a 2 in column 4? I'd have to put it there. That's the only place. But now, look, I need to put a 5 in column 4 as well. And there's nowhere for it to go. There is no valid space because there's definitely a 5 in one of those two squares. So there can't be a 5 in the same colour. So look, we actually are able to deduce that there must be a 7 and a 2 in this region. Therefore, there is no 9 and 4 in that region. Oh, hang on 1 second. Sorry, we just had a necklace emergency. Right, so we just deduced that there was no 4 and no 9 in the red region. Now, what can we do with that? There must be something I can do with it. Well, one thing that I can do with it is this 4 suddenly becomes a little bit better on this box, look. Because if these can't be 4s, this can't be a 4, and that has to be odd. I can pencil 4s in there. Now, yeah, okay, well, it's not brilliant, but this 4 and this 4 now operate on the central box because I can't place 4s in there, there, or there. So I get a 4 in one of those two places. Now that is nice because that forces that to be a 6 and that to be a 4, which, well, it removes 4s from those squares and, oh, it does get me an 8 down there. So that means that's a 3 in order to make the parity of this one work. So now there's a 3 in one of those two squares. Remember, we need to include a 3 in the red region. So once we know it's not here and it's in neither of those, it must be in one of those two. 6. Okay, so must have to use the fact there's no 9 in here somehow. 4, 9, 14. 8, 12. Hang on. Right. Look at the 4 region here. So we've got one even digit in it. We know it's got a 4 in it. What's the other even digit? And in particular, can it be an 8? Well, it could be an 8 if the 8 was there, but that would give us 2 even digits summing to 12, so I'd need 2 odd digits summing to 12. Well, the options would be 3, 9, ruled out, 5, 7, ruled out. So there is no 8 in this region. So that means that the 4 is either partnered with a 6, and therefore there would have to be 1, 6, 1, 4, 6, 9 in this quadruple, which looks possible actually. 4, 6, 9. Or it's or the 4's partnered with a 2, in which case it's going to be 1, 2, 4, 5. So there's always a 1 in there, but I don't actually think we get anything better than that. Bother. 7, 9. This square now, look, that's got to be a 5 or a 9, because it can't be a 1, it can't be a 3, it can't be a 7. So 9, 4, 9, 4, 4, 7. Now, look at this blue region in here. Now, if there is a 9 in this blue region, it has to go into one of those two squares. So let's just imagine we've got a 9 in here. What is the other odd digit that can accompany the 9? We know there's going to be 2 odd digits in this 5-cell region. So 9 plus 1 would give 10. Now I have to make the 3 even digits sum to 10. That's impossible, because I'd have to repeat a digit. I mean, I'd have to repeat a digit even if there isn't a 4 in there already. But you can see, as there's a 4 in there already, the only way of making 6 would be with another 4 and a 2. So 1 doesn't work. What about 3? Does that work? Well, there can't be 3 because we've got a 3 in one of those two squares. 5. 5 doesn't work because this square has to be a 5 or a 9. So if I put a 5 and a 9 in the blue region, that square is broken. So the only option left is 7. But that makes 16. And I can't make, given I've got a 4 in here already, how do I make 2 even digits add up to 12? I can't unless I repeat the 4. There is no 9 in this, in the blue region here. So 9 is in one of those 2 squares. That means that one is a 9. 3 9s. Are these all 9s then? Well, I can't assume that's the case, but that is very odd. I suspect there'll be mathematicians cleverer than me who can say what's going on here, but I don't. It's an interesting thing to note. Right, so this 9 here, what is that telling us? I tell you what it tells us. It tells us that there must be a 7 in this blue region because there is no 9 in it. And that's because if we just try and include 3 and 5 in here, we've then got to make 3 even digits add to 8, which is just completely impossible. So there's definitely a 7 in there. And there's no 3. And we know there can't be a 1 because 1 and 7 is 8. 3 even digits can't add to 8. So this is actually a 7, 5. 7, 5 is 12. 4, yes, 2 and 6 works. That's the only thing that works in this box. So it's got a 5 in it. This elbow thing has a 5 in it, so that does place a 9 in the middle. It's so tempting to put a 9 in there. I won't do it. This square, therefore, is... That one can't be a 7. These 3 can't be a 6, so there must be a 6 in one of those 2. Is that useful? Well, it might be. I think I'm going to have to change my notation here. I'm going to change it to this. So in this box, I need to include 2, 5, 7, 4, 6. So this is not 4. This is not 7. None of those are 6. There's definitely a 6 in one of those 2 squares. These 3 squares have got to be 1, 3, and 8 to complete the box. That one can't be a 3 because of the 3 up here. And that one can't be an 8 because of the 4 box. If I put an 8 in here, I've got 8 plus 4 is 12. And I've only got a 1 as one of the odd digits. And then 1 plus 9 is 10. That does not equal 12. This is a 1. Therefore, we get a 3, 8 pair here. That means that one's an 8 just by Sudoku. No 8s over there. It's sort of almost got a unique dominoes thing going on there, look. Well, especially as that can't be a 1. I rather suspect we're going to find that this is all... Well, the other thing that could happen is that this just... it avoids the problem by adding up to a number that doesn't... Well, there's got to be an 8 in one of those, actually. So do we have to have the fact that that is a 7 then? Well, we won't assume it. Let's carry on. So we've now got... we've made a bit of traction, or a bit of headway. So we can presumably, given we've got very limited options for this 4 cage now, are we going to be able to... We've got a 1 in there. It can't be a 9 or a 3 that's accompanying it. So it's got to be a 5. It's got to be a 5 as the other odd digit. So it must be 1, 2, 4, 5 into these squares. So this is a 2, 4, 5 triple. That's not 2, that's not 5, that's not 4. This square is therefore a 6. This must be 1, 6, 7 to complete the box. That's not 7. That must be 2 or 5 to complete the column. Still need to put a 1 in this box. So this is a 1, 2, 5. Or 1, 2 and 5 are the options up here, look. What a puzzle. Now also, look. What do these squares have to include a 2? Because we haven't put a 2. We know there's a 7 and a 2 in there. There's got to be a 2 in one of those. There's a 2 here. We get that. That's a 2. That's a 5. The 5 fixes the 4. That can't be a... Oh, that can't be a 1. These two squares have got to be 6, 7 and 9 in some order, just to complete this row. Oh, of course, and this region, this 8-cell region, well, we know it's missing a 5, but it's got every other digit in it. So this 2 must go there. There must be a 2 in the blue region. So now... Well, there can't be a 2 in a 3-cell region, so there must be a 2 in one of those two squares. That can't be a 2 either. The 2's are starting to get interesting, aren't they? Look, 2's have got to go here, therefore there's no 2's up there. Ah, yes, look. 2's are locked into row 1 and row 2 in this box. In this box, 2 can't go here, so 2's are locked into one of these two squares. So, also obviously in row 1 and row 2. So we've got enough 2's now in row 1 and row 2. This square can't be a 2, that fixes a 2 here. Now, look, yeah, this is nice. Look, there's a 4 and a 6 in row 4. So we know that this square is odd. So the 4 and the 6 are both in the T-shaped region. So now... So 4 and 6 add to 10. So we need 2 digits, 2 odd digits in here to add to 10. So either 1, 9 or 3, 7. But there's no 5, therefore, in this. Ooh, yeah, look. There's no 5 in this T region. There's a 5 here. So there must be a 5 in one of those two squares. Ooh, that's nice. Look, 5's here. See that one? That must be a 2 now. That makes a 5 up there. None of those is a 2. This 2 sees that 2, so that's not a 2. This must be a 2. 5 now can't be in either of those squares. 4. So if we look at this row, we've got 6 digits now. We need 4, 5 and 8 into those squares. Now, I remember there's a 5 there, so look. 4, 5, 8. Four here, that can't be a 4. I feel like we're right on the cusp of this, of finishing this now. Come on. We've got more restriction on the 1 region now. So what is the other odd digit we're putting in this region? It can't be a 3. It could be a 5. That would give us 516. Looks possible. 516. That's one option. It can't go with a 9, so the only other option is 178. That would, now the 8 would then shift there. So this is never a 1. This square cannot be a 1. It's either a 5 or an 8. And this is a 167 triple then. Oh, sorry, 167 triple. 5, 8. Ah, so the 1 is here. It's in this one of these domino. Well, it's in this domino, so that's got to be a 2. That's a 1. That can't be a 2 now. So the 2 can only go there in this pentomino. And my pencil marking seems to suggest this has to be a 9. Is that true? So we've got 4, 5, 8, 9 to place. Why? Oh, it can't be a 4 because of that. Yeah, that is a 9. And then that one would have to be a 4, would it? Yes, it would. So this, good grief. So there's a 5, 8 pair now in this P pentomino at the top. Now that must be useful. That places an 8 in one of those two squares. Four, 5, 8 triple in this box. There must be a 9 in one. There must be a 9 in one of those two squares. Actually, we've had that available for a while. No. Look at this square. Now, this, if we make this square a 4, this box becomes forced because we've got two odd even digits adding to 6. So we need to put 1 and 5 into those squares. But we know there's a 1 up there. So this square's got to be a 5. But it can't be a 5 because we know actually we had a 4, 5, 8 triple in this box. You can see actually it's going to force both of those squares simultaneously to be 5. So this is not a 4. This square is not a 4. That gives us a 5, 8 pair here. This can't be a 5 now. That means the 5 is there. That must be a 4. 5, 8 pair there. 5, 8 pair there. This is 6, 7, 9. So close, I think, to cracking this now. 5. Oh, 9s, of course. Look, 9's here and 9's here. So we've locked 9's into the same two columns of the grid in this box and this box. So that can't be a 9. Gives us a 9 in the corner. Now, well, actually we can just look at whether this can be a 9. That's one thing we can do on this box, because there's a 5 in there already. If we add a 9, that makes 14, but we've got a 4 in there, so we can't get to 14 with whatever we were to put in this square. This is not 9. This is 9. Now this box is getting constrained, isn't it? Because same thing again. If we make that a 5, it's too big. This has to be an 8. That gives us a 1 here. That gives us a 1 here. This is a 5. Therefore, that must be a 6. That fixes the 6 and the 7. This is a 7. Now we've got 12. This has to be an 8. This has to be a 7. That can't be a 2. We've got a 4, 5 pair here. We can finish this. Look, that's got to be a 3. The 3 fixes the 3 and the 1. That fixes the 3 and the 1. The 3 fixes the 8 here. So these... That must be a 1 now. This has got to be a 7. 8, 3 is fixed here. Oh, now. Yes, look. This square has to be odd. And it can't be 1, 3, 5 or 7. So it is 9. These squares, that's not 9 therefore. I need a 3 and a... 7 must go here just by Sudoku. There's a 3 in one of those squares. Let's check. Yes, it does work. 3 plus 7 equals 4 plus 6. The 4 fixes the 4, 5. Those two squares have got to be 5 and 6. There's a 5 up there, so we're still okay. 5, 6. This is a 6, 8 pair. These two have got to be 7 and 9. It's still working. Yes, 9 here. Seven. That fixes the 6. Fixes that as a 7. Something should get ruled out from that one. Look, yeah, that's a 3 or a 6. No, that's only a 6 actually because of the 3 at the top. That forms a 3, 4 pair here. We need a 1 to complete column 3. The 1 and the 6 resolve. The 6 and the 8 resolve. 8 into one of those squares and it goes with a 3. Oh, please don't have made a mistake. So these two squares have got to be 4 and 7. Yes, it's going to work. 7 goes here. 4 goes here. 4 goes here. 3 goes there. 3 goes there. 8 goes there. Oh, I can fix that up there. 8, 5. Submit. Yes. Wow. Oh man, that was incredibly interesting. What a puzzle. That you can create a puzzle with that constraint that has that beautiful, beautiful logic in it. It's another massively long video, but most of the comments seem to say that you don't mind that if the puzzles are worth it. And man, was a puzzle like this worth it. Let me know in the comments what you thought, and we'll be back later on with another edition of Cracking the Cryptic. Thank you, Christoph Seeliger, yet again. Brilliant.